we're going to do a washers problem. This is a washer right here. It's this area, and the area is actually pi r squared, but it's big R squared minus little r squared. So big R is the big radius, little r is the little radius, and we're finding the area in here. And they call this thing a washer because it's like the thing you put on a bolt when you have a bolt and a nut. So it's called a washer, and what we're going to do is imagine a stack of these things for this solid. Well, let's see the whole problem from the beginning. The book will write, or I will write, something like this. They'll give you a region with a recipe, some equations of curves. The area bounded by them is what, and then it's rotated around an axis. That's what makes the solid. So y equals x squared, that's the parabola looking piece. Only I didn't draw the full parabola. I only need the one in the first quadrant. So there's this piece in the first quadrant bounded by x equals 3. Y equals 0 is the x-axis. And then that gets rotated around the y-axis. So you got to try to imagine it. So here's what I used to do when I was in college. I would cut out a little piece of paper, you know, and let me see if I can get that position so it looks about right. Here we go. There we go. So there's the region, and we rotate it. Rotate it around. Now you can kind of, I hope, see the shape. So it's a dog dish. Here's where the water would be. We're finding the volume of this part. So we take these slices perpendicular to the y-axis, and each of those slices has this shape, except the very top one is just a ring. It's just a circle. The very bottom one is a flat plate, but everybody else has a hole in the middle, and the hole, the inner hole, that little r, rides this curve. So that's the first insight to make, is that little r is this dude. That's little r up there. So little r is equal to x, because you're measuring from the y-axis across. You know, when you measure from the y-axis across, that's an x-coordinate. But since my cuts are perpendicular to the y-axis, I have to do a dy integral. So when I have little r equals x, I actually have to have x equals square root of y. And that's how the personality of the curve part gets into the problem. That's how, because if you think about it, you know, what's going to say what the volume is? It's this curvy part on the inside. The outside is just a straight cylinder. But this inside curvy part has to have a say in the integral. So here's what a washer problem looks like when you're perpendicular to the y-axis. That's why the dy. So then I substituted in big R stays 3. This is big R right here. Big R stays 3. It's constant. And then little r was square root of y. Little square root of y gets squared. So I get a regular 9 minus y here. And then you integrate. You're ready to integrate. 9y minus y squared over 2. And the final answer is 81 pi over 2. When you do this last subtraction, you get 81 pi over 2. And that's the final answer for that dude. And that's how you would do a washer problem. We're now going to do a washer problem that's got a little bit of a twist to it. All right, we're doing a different one now. We're going to have the region rotated around a line, a vertical line, that doesn't bound the region. So I'm going to rotate that region up there around the line x equals 4. So there's going to be that gap in between. And it makes a shape like a tree, Christmas tree stand or a volcano. That's the shape we're going to make. So try to imagine it. I have to put down the ferret. Let's get one more shot. Oh, there she is. Now, here's the shape. And we're going to rotate it around that line. Trying to keep that line in position there. Primitive man making a solid. So the tricky part is not the little r. Little r stays constant. Little r is just 1. Big R, that's the toughie. To see big R, the best thing to do is to draw in this little piece here. that distance you're measuring from the y-axis, that's just x. So big R is 4 minus x. But because my slices are perpendicular to the y-axis, I can't use 4 minus x. I've got to use 4 minus square root of y. But now I've got big R. But that's the toughest part. That's the toughest part. There's also a little wrinkle over here when we go to solve, when we go to set it up. Because when you do big R squared minus little r squared, the big R squared is now a binomial because of the subtraction. So multiply it out, and don't worry. I mean, this is just y to the 1/2. We can integrate y to the 1/2. So trying to finish this in the space provided, I have to erase to the side here. Let's see if we can finish this off. And now it's just a slightly nasty integral. So you can have a pi. 16 minus 1 is 15, so that's a 15y. I'm going to do the integration in there. Negative 8y to the 1/2, that becomes negative 8y to the 3/2 times 2/3. And I have y, that'll be y squared over 2. Still got to evaluate from 0 to 9. But we're in luck with that 0 to 9. 9's a square, so when I go in here, I can take care of that 9. And then putting in 0 makes all of this 0. So I can just do the 9 now. So I have pi times 15 times 9. That's 225. And then I have 16 thirds. Let's just write that down. 16 thirds. And then it's 9 to the 3/2. Well, 9 to the 3/2 is, you take the square root of the 9, that's a 3, 3 to the 3rd, which is 27. Well, I'm going to cancel a 9 out of there. And then I get a fraction that survives, plus 81 over 2. So final calculation, I've got a 225 minus a 144. I guess I can fit it right there. So it's pi 225 minus 144 plus 81 over 2. So let's see, that's going to be 1, and then 22 minus 14, I think is 8. So 81 plus 81 over 2. Wow, that's kind of nice. 81 plus 81 over 2 makes me feel like I'm doing it right. So that's going to be 243 over 2. 243 pi over 2, and that's my volume. And that's how it goes. It's a long story. I hope you don't mind. But that's what we did. That's where we are at the end of, say, November 7th, 2020. All right.